You need the fact that the difference is you have a minimizer for the difference. And also, again, you all see why this, if this is, again, assume a bunch of stuff, you need this to be differentiable in the neighborhood of theta equals theta star. All right? And because theta star is a global minimizer, it satisfies the conditions for optimality. Right? Okay, so getting a global bound like this is a lot stronger than just saying it's a stationary point. You know, it's a lot more structure. You know, so it's given this, you can very likely say that you've got bounds in the derivatives as well. So you can take higher order derivatives and play around like that. Because just a stationary point can be awful. Instead of a local max, it could be a local min, and this is going to rule out a local minimum. I think, for example. Yeah.
And then you're able to take that relative entropy term there with the theta star was because the limit argument up there?
No, we haven't done it yet.
Okay, so
Yeah. What I'm trying to say is that I've jumped to the end of the proof, and the end of the proof is way more informative. This is way more informative than this. And so we have to prove this, and that won't take long. Okay? Yeah. As long as I don't, as long as I'm careful. So let's go through this. So I've got a subsequential limit of these theta ki's, and we're going to assume continuity. So again, I said a bunch of stuff, continuity. So, I should log. Okay, so this is basically I could exchange the limit and the function. That's the definition of continuity. Just take the limit inside, and theta ki converges to theta star. That's the definition of continuity with respect to theta. Okay, so we need to assume this is continuous. Just write that. But we also know that this thing just converges. This again was monotone. It's non-decreasing. So any subsequential limit is going to be the same. It's just increasing. So this we already knew this converged to some limit, which could be infinity. Assumption it's not infinity. We'll assume it's not infinity. And so basically there might be many subsequential limits, but this limit will always be the same. They're all the same. Because it converges. I don't need to take a subsequential limit of the log of the likelihood. We already know that converges. Clear? We knew this converged from the start, or when we proved this lemma. A monotone sequence is convergent. All right. Cool. Okay, and so then we do a common trick. Is we leverage this. Okay. So this is convergent, and it could be, and it's monotone. We're going to exploit monotonicity to say that the thing that we're interested in, the log likelihood at stage k, is the log likelihood, log likelihood at stage 0 plus the sum of differences. I'm just looking at telescoping series here. But the point is these are all non-negative. All right? And this is converging, so the delta i's go to 0. All right? So basically this limit is just the sum of all the deltas. All right, so the difference of the likelihoods goes to, log likelihoods goes to 0. Clear? Yeah. This is convergent. These are non-negative. So I've got a partial sum of non-negative numbers, which converges. The terms have to go to 0. Otherwise, I'm summing. Oh, yeah. All right. So how do we put this to use? We're trying to get here. So let's go and monkey around with that. Yeah. So we get to the big step. I guess I can kill this. Can I kill this? It's so amazing. So I've got, this is my goal, and all right, so what we're going to do is we're going to try to play with that goal. I'm going to take this minus all this crap pretty much. So I'm getting there. So I've got this on the left-hand side. I'm trying to prove this goes to 0. But what I've done is I don't know anything about theta star yet, or not much. So I'm plugging in theta k. And anybody see a bound on this? Anybody tell me what that max is? What's the maximizer, everybody? Come on. Yeah. Oh, theta k plus 1. And so. And I'm going slow, so somebody will call it out. Trying to get a bound like that, you know.
The difference between the walls, right?
Well, I've got, no, but this looks familiar, doesn't it? I've got that difference there. It looks like, yeah, see? So that looks like it's delta k plus 1. Yeah, it's what I just called delta k plus 1. But this again is negative, right? You know, or less than or equal to 0.
Upper bounded.
So now I use continuity again. So I got an upper bound which goes to 0. QED. That's it. Because basically what I've done is I've got the, basically I've got this thing for every k is bounded by this. So if I take a subsequential limit of the theta ki's, the theta ki's go to theta star, that goes to theta star, that goes to theta star, and so I end up taking the limit and getting this bound. You know. So again, I've established this limit for every k with theta k for any k. So then I take a subsequential limit, and I get the bound. Yeah. Yeah. This is just the bound I care about. I mean this, yeah. I want this to be less than or equal to 0 with theta k replaced by theta star, right? Instead I'm getting it less than this delta k plus 1, take limits, done. So it's beautiful. I mean, if you don't think that's beautiful, just, I don't know what's wrong with you. See a math therapist. I mean, the fact that you can fiddle around with this, and it's such a simple proof. I mean, it's, what did I do? I mean, monotonicity was just a matter of realizing relative entropy was hiding under the surface. And then, it takes some thought to see that if you can get the right kind of bound, you can get the stationary point property. Right? Yeah. Right. But again, that's all you get. Okay, so in practice, something funky could happen. So it's 4 o'clock. I need to get a bit of water. Let's take a little break. But and anything unclear here? Some of you looked like what? QED? You don't speak Latin? I don't know. Yeah. I'm going to get a bit of water, and then we'll march on.
So what is the biggest assumption?
What's that? Oh, yeah, well, yeah, so what did we assume continuity. And the thing is that, maybe we don't care about this. So basically, we never, ever needed the smoothness. Basically, to get this upper bound, all we ever used is continuity of everything in sight. And so the only reason to impose smoothness is that somebody reading would not see this as a really valuable bound. So if I impose differentiability, then I can show that this implies this. But I feel this is a much, much stronger result than this. So to me, this is the endpoint. So there's only one assumption. It's continuity. It's very, very, very nice result. The continuity to get this bound, then smoothness to get this. Cool. All right. So let's brief break. Oh yeah. So go.
So there is an entropy term in the Q.
Yeah.
So the maximizer doesn't matter.
Oh no, the thing is that I'm just trying to prove that bound, so I threw that away. Oh yeah, it didn't depend on theta. Oh yeah, I see what you're saying. The thing we were maximizing before was this minus an entropy, but the constant didn't depend on theta, So basically the maximizer is the same, So thanks for pointing that out. Yeah. Yeah, this is not our objective function. It's just the part of the objective function that depended on theta. That confused me. I remember when I first read this proof, that was the point I got stuck at. So I remember that.
I
Yeah.
just want to clarify on that.
Yeah.
Open door to that bound
Yeah, we never used smoothness. It didn't occur to me. Well, we never, did we ever use it? See, I said assume continuity here of this, and I used that to get this.
And that's what you use.
Yeah, and then I'm using that throughout here, you know, and then from here, then I'm saying assume here I say I have to assume all these guys are continuous because I have this bound for each k. I want to let k go to infinity, and I want to replace theta k by theta star. That requires that this be continuous and this be continuous again in theta, right? And then I get this magical bound. So smoothness is only required to go from here to there.
And then the sum of deltas is finite because of continuity.
No, well, no, actually, let's think about this. You know, this is standalone, you know, and basically we need it to be finite. So basically, we know this converges because we proved monotonicity, right? So the assumption the limit has to be finite. It's on infinity. Oh, yeah.
Something is increasing, it will even go to infinity.
It could go to infinity. I mean, yeah. So that's assumption number two. Two important assumptions is continuity and the limit is finite. Yeah. So this is not an unbounded sequence.
So yeah, the limit is finite is the assumption that I said.
Yeah. So there's really only two assumptions in all of this. You know that this is bounded and that this is continuous. Yeah. Yeah.
You also said that those deltas are not negative.
Yeah.
Can't the log of probability?
No. Remember, this was the lemma. Go back to your lemma. We proved that this was greater or equal to this.
Yeah,
That lemma was erased.
that's true.
So this is greater than this, so that by the fundamental theorem of subtraction, this is positive. Okay, we proved that this was greater or equal to this. It was the one-line proof.
Okay.
Yeah. Okay. Yeah. All right. I'll accept more questions, but I gotta get some water. Yeah. All right, it's all crystal clear?
You know this is taught in the machine learning course.
What's that?
Machine learning.
What about it?
This is taught. This algorithm.
Oh, I don't know. I'm not sure I understand. I mean, EM is a standard statistics tool, so it's taught in lots of courses, so I don't understand. What's your question?
Oh, it's taught in a machine learning course here.
Oh, of course, yeah. No, EM is everywhere.
But it's not derived like no hidden Markov model.
Yeah. No, EM is, you'll find a lot of courses on campus, yeah. I mean, yeah. So, no, definitely my goal here, again, is to teach you how to think about these algorithms and how you can understand them, you know. So, like I said in the beginning, I would never even get into this if I couldn't give you some structure, you know. Like, I have such a hard time giving a course on neural networks. You know, here's an algorithm. Try it out. I mean, you know. All right. Well, oh, I see. Well, I mean, remember, this was just, in this case, it just came out of nowhere. Yep. There's this insane fashion over the last decade or more, 15 years, on designing regularizers to get certain properties for the limit. And and actually, I mean, it's like, there's this, Joram Bresler at Illinois back in the 80s was pushing for L1 regularization, and nobody would listen to him. And it's so strange that Berkeley got all the credit and Stanford. You go back and look at old papers by Joram Bresler, he was pushing for that. It's a strange thing. Just the computers weren't ready for him yet. You know, Okay, so shall we at least start Baum-Welsh? So let me see what I want to say here. Okay, so the same notation we've used in EM all along, but also the same notation we've used for hidden Markov models. So we have an observation process coming out, and there's a hidden Markov model, Z, hiding there. But now there's a parameter theta, but the parameter theta is everything. We're assuming a time homogeneous Markov chain, to make things easy on ourselves. And we have our output measurement matrix B, as before. PZ1, we're going to simplify notation. Hayek calls it pi. We'll just call it pi. We just, we don't, too many letters there. And we want to estimate all of them based on measurements, right? And I don't know if this is ever done in situations where there really is. Well, I should be careful. I think most applications, there's no hidden Markov model. You just have data, and you're trying to fit a model, And it's very likely that the state process you get has no interpretability. It's nothing at all. But in control applications, that's not true. In control applications, you really typically have a state you really care about, and you want to try to design things so you get, so you can have an interpretable Z, so it means something, and the homework is going to be that flavor, Now, what if you, for EM, what if you knew everything? Or you observed everything? Think about it. What would you do? And for simplicity also. For simplicity, we'll just take the labels to be 1 through n for the Markov chain, and 1 through m for the observation process, just take integers, rather than using the little lowercase z's and all that. But can you imagine how easy this would be if you, if you could observe the whole process? What would you do? Think about it.
Add in a minus KZ term to parameters?
No, I'm talking about just intuitively. No, forget, you never took this course in your life. What's that? How about pi, PZ1? What would you do for everybody? You just Monte Carlo, yeah. So my pi hat, say, of j, I would just take it to be, I have 1 over t, some k equals 1 to t, of the indicated function that z1, k, not k. Wait. Hold on a second, I'm getting myself confused. Wait, stop, erase that. And even my notation's not set yet. Pi 1's a problem, actually, I take it back. I shouldn't have jumped to pi. Pi would be hard. I would need multiple runs. Pi, I take it back. Without getting repeated samples of the Markov chain, I'd be dead. So now forget about that. What about B? Okay, now to your sampling point. So again, I didn't have enough data to get pi. I would need a prior. But for this guy here, I've got a lot of data because I've got a lot of samples. So we write this out as the probability that yk equals j and zk equals I divided by the probability that zk equals I. And so tell me your p hat. You definitely had it. So just how would you estimate this?
I mean, just take a sample mean.
Yeah. So you just take the sample mean. Okay, and so you better have a lot of data, as hopefully you've gained from the previous lectures. If there's a lot of memory in this process, then in the Z process, then you might have to take a lot of data to get reasonable estimates of this. And you're divided by something that's maybe very small. You've got maybe a lot of variance in this, but that's it. This is the optimal estimator for B. A is also a conditional probability, so you get the same sort of formula. So the only thing here is pi. You'd need a prior. What? Oh, I need repeated observations. So here, I just watch the thing evolve in time, and I've got it. Here, I would need somebody to perform repeated experiments with time 1 repeating over and over again. It may be that time 1 just happened once. Time 1 might be physical time. You know what I mean? So this depends on the setup. Imagine a finance problem where this is, I don't know. No. I said in the text. I'm just trying to keep the notation as the text, so that when you read the text, it'll be the same. He used pi for the prior. For Z, so it's not stationary. Yeah. If it was stationary, that'd be quite nice. Yeah, if we knew that we were watching a stationary process, you would just compute the estimate of the transition matrix for Z, compute the stationary distribution, you'd be done with it. Yeah. Or take the empirical averages. All right, cool. But we're not going to have that. So we're gonna try to estimate this. Okay, so we only have Y. We apply Baum-Welch off the shelf, and parts of it are tedious, like the Kalman filter, which I'll skip, and parts are absolutely beautiful. There's only a few things that are a problem. in so for the E step, it turns out we need everything that we've looked at. We need the probability that Z equals Z given Y equals Y. And I'll put in here comma theta, you know. That's the smoothing property. I should put a theta k there, okay? You know, basically to get the kth, have the kth model, we have to compute an expectation. Things like this come up. All right, so basically just that. That doesn't come up directly today or Thursday, but it does implicit in somewhere. But unfortunately, there's also things that I never ever talked about. I'll give it some notation here. Okay. Well, you don't have to feel like secretaries. This is right out of the textbook, so you can just, you know, read it there. Now, have you guys learned about this? It's see here. You know, here I was trying to look at the probability of an entire string for any z. Look at look at the probability of the entire string. We could get this from this, right? Because you could marginalize, you could sum out everything else and get this from this. So this does lead to these two guys, but computationally, it's a nightmare, you know, to have to compute this entire massive thing. You know, Z might be a string of 10 of a million symbols, you know, and then to come up to come up with this probability of a million symbols and sum over all the terms except two, you know, corresponding to t and t plus 1, for every t would be awful. So this goes to something I didn't cover. So there's something big in signal processing, which is a Viterbi algorithm, where you're trying to find the basically this maximum likelihood decoder in communications and signal processing is a beast itself. And the way you compute this is through Viterbi's algorithm, which involves this what's called a forward-backwards algorithm, which involves things like this. So there's a whole computational machine, which I didn't present. It's in the book, okay? It just doesn't have the concepts that the EM algorithm has. That's why I'm not covering it. Okay, so you could just look it up on Wikipedia or the book. All right. So these things you can get it. You can get an M file off the web and run it. You know. All right. And so I don't know if we're going. I think we're just going to start this, but let's just think about it. what would the E step be? What is the, I've got the complete data is everything. And what's the probability of the complete data? It sounds horrible at first, but it's nothing. Think it over. What's the probability of everything? And so you give me a string of y's and a string of z's. Remember how simple the probability it was? Remember how we derived the smoothing algorithm? We looked at this thing, the probability of the joint thing. It was just a giant product. And then you take the log, it's a giant sum. Okay, so you get the log of the prior.